So it's a pleasure to welcome Adam Thompson of the University of Queensland, who will speak on new examples of Ricci solitons with non-compact symmetry.
Perfect. Thank you, Carolyn, and thank you for allowing me or inviting me to speak here. Yeah, I'm quite excited to share this. It's kind of my first bit of research as a mathematician, so it's a fairly big moment for me. Yeah, so as Carolyn said, today what I want to talk about is some Ricci solitons with non-compact symmetry. And so I'll give some definitions and hopefully some motivation, but I guess just to start with, the main motivation or the main inspiration for the project was the fact that there are, outside of the homogeneous case, a lot of Ricci solitons known where there's a compact symmetry group acting, for example, ON, so rotational symmetry, but there are far fewer examples where this symmetry group's non-compact. And so that's the main goal of this research, to start to try fill that gap. Okay, and so the main objects I'm going to be focusing on are going to be gradient Ricci solitons. Okay, and of course, here, this is a triple, where I have a smooth manifold equipped with a Riemannian metric, and it should satisfy that its Ricci curvature is some multiple of the metric plus the Hessian of this function f. Here, lambda is just a real number. Okay, and so these, of course, we're interested in these for several reasons. I mean, firstly, perhaps if I just, it's actually much harder on an iPad. If I had a board, I would cover up the Hessian term. So if you just squint, then you get the Einstein equation. And so these Ricci solitons are, of course, a generalization of Einstein manifolds, and particularly in the presence of symmetry where Einstein manifolds might be obstructed, it can be nice to have another distinguished structure on a manifold that sort of generalizes this condition. And then secondly, of course, and perhaps more importantly, Ricci solitons appear in the context of the Ricci flow. And so these are actually kind of the generalized or the geometric fixed points of the flow. And in particular, within the Ricci flow, actually, sorry, I was going to say something else first. So for my purposes, I'm going to be interested in the expanding case. Okay, so this is the case where my constant lambda here is less than 0. And in fact, throughout this talk, what I'm going to do is I'm going to fix lambda to be -1, since I can scale. Okay, and so when we're talking about expanding solitons, their context within the Ricci flow is that, among other things, they can appear as the long time limits of the Ricci flow. So expanding solitons exist on an infinite time interval from when they start up to infinity. And so perhaps if you have a Ricci flow and it has nice enough properties and it exists for an infinite amount of time, if you look at the limit, you should perhaps expect to see an expanding soliton appearing. Okay. And so that's just the general context where my talk is going to sit. And so given these Ricci solitons, of course, there's been a lot of interest in these over the years. And so people have come up with many examples. And in particular, a nice way to generate examples is by enforcing some type of symmetry ansatz. And so in particular, many examples have come up with this following. So there are many examples of these Ricci solitons. Where we're going to assume that they're invariant under some compact group action. Compact G. Okay, so for example, a cigar soliton. I don't know where that went. So this looks like, of course, a cigar. Just make sure I get the ending correct. Something a little like that. It's rotationally symmetric. So there's kind of an O2 action there, which is compact, of course. And then there's the higher dimensional analogs. So your Bryant solitons. These are invariant under, of course, an ON action. And I could go on and list a lot of these examples where there's compact symmetry. So over the past kind of 20 or so years, there's been a lot of interest here, and there's been a lot of great examples that have been generated. But conversely, if you kind of flip to this other side where you ask, well, how many examples do we know where there's a non-compact symmetry group assumed to be acting? And the examples are a lot more difficult to find. Okay, so not many complete, I'm going to put in here, examples with non-compact group. Okay, of course, in the homogeneous setting, we have a lovely large class, namely the solved solitons. Okay, so in homogeneous setting, solved solitons. But really, when I'm talking about not having many examples, I mean beyond this homogeneous setting. Okay, and so my main aim with this research has been to fill this. Okay, to fill this gap, or perhaps filling the gap's too big of a goal, so it's to start to fill the gap, or just to provide some examples. And to that end, I'll say kind of the main theorem that I came up with, which is doing exactly that. Okay, so theorem. I find that if I take a solved soliton, and I'm going to have to assume that the underlying group is unimodular, so let SG be a unimodular Ricci soliton solve manifold. Okay, so when I call it a unimodular Ricci soliton solve manifold, I just mean that the group S here is unimodular, the solvable group. Then there exists a one parameter family of S invariant complete pairwise non-monothetic spanning gradient Ricci solitons on R times S, which I'm going to call M from now on. And furthermore, in this family, I have that exactly one of them turns out to be Einstein. Simply one is Einstein. Perfect. Okay, so as I said, this is kind of my main theorem, and my goal for the rest of the talk is essentially to talk about my process of coming up with the ansatz that I use to come up with these, and why I was motivated to consider kind of metrics of the particular form. And then I'll give some kind of indication of what goes into actually showing that these are complete. And then maybe if we have some time, I'll talk about perhaps the asymptotics at each of the kind of the R ends of these. Yep, so that's there. And I'll just remark here quickly. Remark that the soliton potential, so these are gradient Ricci solitons, so I have a soliton potential. F is going to turn out to be S invariant, essentially by assumption, is S invariant in my case. So if I have a co-compact lattice in S, then what I get gives solitons on and what gamma. And these are going to have kind of two non-compact ends, but the orbits are going to be, oh, sorry, not the orbits, n-1 directions are going to be compact, and then there's going to be the two compact ends. So perhaps I'll draw it look something like this, where I have some compact fibers here. So yeah, this gives us some examples where we have these non-compact ends. Great. And so from there, I'll just start with an example where I fix a particular S, just to kind of demonstrate what the theorem gives in that case, and it'll also give me a chance to kind of mention some of the previously known examples and how my new examples fit in with what was known. Okay, so example, I'm going to take S to be the Heisenberg group. So that is upper triangular matrices, 3 by 3. Okay, and so this is actually one of the Thurston geometries, right, appearing in the geometrization conjecture. And the Lie algebra here is perhaps the simplest non-abelian nilpotent Lie group. So it's spanned, of course, by 3 basis vectors, and it only has one commutation relation, and it's that X and Y, I'm going to say, gets sent to Z. And so on this, I can pick an inner product. I'm going to take the inner product. Sorry, I'll go back up a bit. G naught, such that this basis is going to be orthonormal. X, Y, Z is, I'm just going to say ONB for orthonormal basis. And then perhaps you're going to have to take my word at this, but this does in fact give a Ricci soliton metric. So this gives a Ricci metric on S. So when I take this left invariant metric, which agrees with this at the identity, I do indeed get a Ricci soliton. In this case, it's not particularly hard to check, perhaps because we're only working in 3 dimensions on something homogeneous. Okay. And I'll just point out as well that, of course, this also, or S, should I say, S also has compact quotients. So the remark I made before about when we have a co-compact lattice, we get something with 2 non-compact ends, that is valid in this case. Okay, and so previously, what was known on this example? So previously there were, to the best of my knowledge, 2 known inhomogeneous Ricci soliton metrics on when we extend this by this one-dimensional factor. Okay, so these 2 that were known were, there's a Kähler Ricci soliton metric, by Marshler and Riem. Sorry. And this is from 2022. And there's also a quaternionic Kähler metric. Kähler metric, and this is by Cortez, Saha, and Tong. And this is from 2021. Okay, so previously, if I were to look at R across the Heisenberg group and ask, well, what inhomogeneous Ricci soliton metrics do we know on it? We have 2 known examples. There's a Kähler Ricci soliton metric, and then there's this Einstein quaternionic Kähler metric. And so in fact, both of these have special holonomy. And so now what the theorem gives is a 1-parameter family that includes these. And so in fact, the 1-parameter family seems to interpolate between these 2 solutions and then also extend them slightly. So if I were to draw, and so later on, what I'm going to do once I've explained my equations a bit is I'll draw a picture of a phase portrait I get when I do some ODE analysis, and then I'll actually be able to draw where these 2 solutions sat in this example, and then kind of explain how mine span between them. Okay. And so in order to do that, I'm going to talk a little bit about the actual construction of these. Okay. So in order to come up with them, you kind of want to make a nice ansatz that's going to allow you to work with some actual equations. So I guess in general, it could be a very difficult problem, even among cohomogeneity 1 metrics. So what I want to do is I want to assume my metrics have a particular form that I can get a very solid grip on. And then that's going to give me some equations that I can actually work with and hopefully come up with some information from. Okay, so these. Right. Okay. And so of course it's going to be cohomogeneity 1, as I've said, but even beyond that, I'm going to assume something further. And in order to motivate why, or what my particular choice would be, I'm going to take some inspiration from the homogeneous case. Okay, so given a nil soliton, and G0, I'll call it, i.e., so a Ricci soliton nil manifold, what we can do is we can extend this by 1 dimension to obtain an Einstein manifold. And in fact, it's going to be an Einstein solve manifold. Okay, and I'm going to call this GE. Of course, this was done by Jorge in 2001. Okay, and so still this Einstein solve manifold is of course homogeneous, but it's the particular form here that the metric of the extension takes that's interesting to me. Okay, and so just since we have a nil manifold, by assumption, my Ricci curvature of n, or I should say the Ricci endomorphism, if I restrict it to the tangent space at the identity, has this particular form. So I write it, and it comes out to be a multiple of the identity plus some derivation. And so what I do, or what we do, is we equip R times n with the metric GE plus ds squared G naught. Okay, so on each, I should say here, so on each of these kind of R slices, the metric on this n orbit, what it looks like is a pullback of the actual nil soliton metric with respect to some automorphism. So here, phi s is a 1 parameter family of automorphisms such that, and I have d phi s equals e to the s d. And so just so that I'm not working with some ugly constants, I'm going to assume, just for this example, or this point here, that the trace of the soliton derivation is equal to 1. Okay, so I just introduce this normalization. Otherwise, you have to divide this t here by something. Okay. So that's what these look like. And so it's this particular form of a metric that I'm going to latch onto and that I'm going to use to try come up with new examples. And so what I'm going to do is I want to consider metrics on R times S of the form bs squared plus c squared g naught. So with c being a positive function and h just being a function. Okay, so essentially what I'm doing here is I'm taking this form of this one-dimensional extension to an Einstein solved manifold, and I'm going to re-parameterize the speed at which I'm pulling back these metrics, and then I'm also going to allow for a little bit of scaling of the orbits. And I should also say, and soliton potential, I'm going to take f as also only a function on the R factor. Okay, and so with this, this form of the metric, I can calculate without much difficulty, can calculate the shape operator of these hypersurfaces, or the n orbits. Sorry, I wrote it in. I'm back to F. Sitting inside here. And then using the Gauss equations, of course, I can express my Ricci curvature in terms of this shape operator and its derivative. And so this gives an honest to God ODE in these variables. And so in particular, since curvature is second order, and I have three functions, I have C, H, and F. A priori, you would expect to get 6 equations. So an equation for each function and an equation for each of their derivatives. Now, in fact, what I find is you actually only end up with 4. And the basic reason for this, so firstly, so like this, so soliton equation gives me this second order ODE system. In C, H, and F. But then if I add a constant to H, it doesn't change my actual Ricci soliton equation. And so really F, sorry, not H, I meant F, the soliton potential. So this is well known, that really it's the derivative of the soliton potential, that's the true variable. And so that takes me down to 5 equations. And then I get a similar phenomenon happening with H. And so if I shift H by a constant, what I find is that this does not actually change the equation. And the basic reason for that is that it corresponds to just pulling this background G naught back by an automorphism, which just gives me another Ricci soliton solved manifold metric. So in the end, my my 6 equations now thankfully come down to 4, which is hopefully slightly more manageable. And so after changing variables, what I end up with is this system. So first order system with 4 equations. And these 4 equations I get look a little bit like, so Z plus 1 minus WX Y prime Z on S naught minus WY to Z S naught. And so the constants here I'll mention, so C naught, S naught are constant, coming from, so these just come from this background homogeneous soliton metric. So you can semi-explicitly calculate them. I'm not actually going to write them down because they won't add much. And then also N appearing here is just the dimension of this. So in the end, I get this system, which 4 equations is of course better than 6 perhaps, but still I don't have much hope of solving it in general. And so the next best thing that I can do is hope to understand at least some of the solutions. And really my main goal here when I'm looking at these solutions is to show that there exist solutions defined for all S in R. And so the reason that I'm particularly interested in solutions that can be defined for all S in R is that these precisely correspond to complete metrics. So of course, if I have an ODE system, I could pick 4 numbers and then get some solution on a possibly very short time interval. But what I really want to search for here is the right initial conditions to get these solutions defined for all S. Okay. And so the idea behind how I do that is this kind of following process. And so I'll start off by saying kind of what my ansatz has brought me other than just getting my equations. So by assuming my metrics are of this particular form, I have immediately a solution that I do know. I know that if I pick my C to be constant and just always equal to 1, and I pick my H to just be H of S equals S, then I should obtain an Einstein manifold. And so what this actually manifests as in the ODE system is a stationary solution. Okay, so one-dimensional extension manifests as a stationary solution of my system, which I will denote by gamma with a superscript S. And then as soon as I have a stationary solution in an ODE system, I can start to linearize at that solution and start to try look if there's an unstable or a stable manifold and understand my solution near that stationary point just a little bit better. And so in fact, amazingly, if we linearize at this gamma s, you find that firstly, it's hyperbolic, which is very nice. And secondly, there's a two-dimensional, unstable manifold at gamma x. And so by definition, if I pick an initial condition within my unstable manifold, the solution starting at that initial condition is of course going to exist for all s less than 0. So perhaps I should write this. If we start in the unstable manifold, I'll get it that my solution is defined for all s less than 0. And moreover, it's going to converge to the stationary solution as s goes to -infinity. So that even gives me a little extra than what I bargained for. But in showing the completeness, really what I'm interested in is that this s is automatically defined for all negative numbers. And so really then all I have to worry about is showing that I can pick some initial conditions within my unstable manifold so that nothing goes wrong as s grows large. So s continues, or the solution continues to exist as s goes to positive infinity. Okay, so and maybe I'll call this 1, 2, 3. What I want to do is I want to find some omega, some domain omega in the unstable manifold, such that if I pick an initial condition in omega, gives solutions defined for all s bigger than 0. And so when it comes to actually picking the omega, this solution, this Ricci soliton that was known by Marshall and Ream, it came in quite helpful there. That kind of guided my choice of what omega should be. So I won't actually write omega down explicitly, but what I'll do instead is I'll draw a picture of kind of what this looks like if we restricted, say, our focus to the unstable manifold. Since that's now two-dimensional, I have kind of a bit of a better chance of drawing it than I do of drawing something four-dimensional. Okay, so yeah. Sorry, I should say as well, what I meant to say is you also find that within the unstable manifold, you can identify two almost distinguished solutions. So firstly, if I assume that my soliton potential was 0, okay, so I reduce my what I'm searching for to just Einstein manifolds, then there's a known first integral in this case, so my system becomes two-dimensional, and I get a solution in that case. That's much easier to find. And this actually sits inside the unstable manifold. So there's this Einstein solution. And there's also a solution where I assume that this C here is constant and just always equal to 1. So the orbits kind of don't scale. And so another property of this omega is that it's kind of stand out as it stands between these two solutions. Okay, so to summarize, I'll draw this picture. So up here, I have this stationary point, gamma S. Here, I have this C identically 1 solution. Down here, I'm going to label this as real hyperbolic space, and then this. And so this solution, it's perhaps a little bit hard to see, but I tried to draw it there with just kind of a little bow. So it's a genuine curve. It's not linear between gamma S and this other point. And then, okay. And so this is my Einstein. And so this picture, this is the kind of picture you get within this unstable manifold. So I start at this stationary solution, and I have coming out of it these two almost distinguished, perhaps not distinguished, but perhaps easier to find solutions. And then what my omega is going to be is this region here that's kind of swept out between them. Okay, so this is going to be my omega. And what I find is that any initial condition I pick within this omega, because it's in the unstable manifold, it's going to, as S goes to minus infinity, get sucked back to this gamma S. And then as S goes to infinity, it has to stay between these two solutions. And in fact, most of them, all of them except this Einstein one, go over to this same spot here. So I'll just point out that this picture could be almost a little bit misleading, since the soliton potential, or its derivative, necessarily has to go to positive infinity if you want your solitons to be complete. So there's a kind of back to the picture, so to speak. The picture goes, this curve here, one of the directions, if I looked, since it's actually should be a 4-dimensional picture, one of those dimensions that I've hidden is going to positive infinity, but it's doing so at a sublinear rate. So it's not blowing up within finite time. Okay, and then the one parameter is, of course, if I just drove along here. So I should say that my one parameter is like a closed interval, or it sits within a closed interval. And just so to finish off, I'll just quickly explain perhaps why I've labeled this point here to be real hyperbolic space. And to do that, I'll just quickly say what the asymptotics are at these two non-compact ends, if say I quotiented out by a lattice. Asymptotics. So say again with compact, it gives me as I said before, this has now two non-compact ends. And so it's interesting in this case to look at what happens asymptotically to the metric as s goes to minus infinity and s goes to plus infinity, s here being the coordinate on the r factor. Okay, so at one end, this is the minus infinity end, kind of perhaps unsurprisingly, given how I chose my solutions. They're all going to be asymptotic to a quotient of this Einstein extension. All to a, I'll put this in bracket. Yeah, so of course I chose my initial conditions within this unstable manifold corresponding to this Einstein extension. So it was not surprising for me to see that Einstein manifold coming out in that direction. But then, so on the other end, we find three different behaviors. And so these three different behaviors correspond to where the solution sits on this diagram at the top. So these two boundary solutions exhibit a behavior, and then the kind of interior solutions here, so the generic case, they also exhibit some type of behavior. So all the ones in the interior have the same or similar asymptotics, whereas these extremal ones exhibit something different. Okay, so for the Einstein one, what we get is we find it's asymptotic to a real hyperbolic space, or I should say a quotient of a real hyperbolic space. Then these so-called kind of generic ones look like a s squared g, look like a cone over a solved manifold. And so here it's not the pointy end of the cone, it's like the opening up end of the cone, not the singular end. And then finally, the case where my scaling function c was identically one, sorry, I get this slightly strange, or perhaps not strange, but this metric that I don't quite recognize as well as these other two. And so those are the three possible asymptotics at the ends. Okay, yeah, and so I'll just finish up here, given that it's 8:50, and I'll finish by saying that with these asymptotics, you get, I guess, what you would expect based on those previous two examples I mentioned. So with the Marshall-Riem soliton, it sits within this interior case, and they indeed found that theirs has this cone asymptotics. And then for the Cortez-Saha-Fung quaternionic Kähler example, that was also asymptotic to this real hyperbolic space at that corresponding end. But yeah, so thank you for having me.
Thank you very much for a really interesting talk. Are there questions? Ramiro?
Just a quick question, Alan. So the construction for completeness on one end, you use the unstable manifold at the critical point, right? So how about
Yes.
choosing the stable manifold? Because it seems like your Einstein solution, for instance, should be like in the stable manifold of the hyperbolic space somehow. If that makes sense, maybe it doesn't make sense because of that, but
So yeah, so you're right that the solution does lie in the stable manifold of the hyperbolic space. So with the stationary point, I was looking at the one corresponding to this one-dimensional extension. In fact, the stable manifold, there is a two-dimensional one, so it would be a valid place to look. The reason I wasn't looking there is that in these kind of particular cases, so for example, with the Einstein one and the one where C was always constant and equal to 1, the entire system reduces down to a system in 2 variables, which I can, of course, plot on my computer. And the stable manifold you could see in that case, and it didn't appear to be giving complete solutions. So the stable manifold for this,
on the other end,
gamma
too, yeah.
S was, yeah, it was blowing up. Yeah, I haven't looked within the stable manifold for this real hyperbolic space to see if there's more solutions around that. The real hyperbolic space is a little bit trickier because it sits with one of my variables. There was a z variable which corresponds to the scalar curvature of the orbits. And so this real hyperbolic space point sits when this is equal to 0. So on one side of it, it's not very geometric because my orbits should be nilpotent B groups with a left invariant metric. So they should have negative scalar curvature, of course. So perhaps on the other side, there would be some, but again, if you plot it in the Einstein case, it doesn't appear to give something complete. Yeah, so really it was because I was just looking for complete examples. I latched onto the part where I could see I had a chance of coming up with some.
So I have a question. It's a very nice talk, thank you. So what is what happens outside the set or omega in this unstable manifold, that functions blow up when you solve, or maybe go to 0?
So definitely I didn't look at this entire unstable manifold, but I looked. So there's somehow an area here which is naturally defined, you know, when I cut up my unstable manifold. And so within here, definitely they seem to blow up. So I would expect, at least in some cases, that they do. I wouldn't expect that you could look everywhere in this unstable manifold and get these complete solutions coming out. Yeah, but I wouldn't like to say there's no more complete ones in the unstable manifold, but certainly if you just leave this omega slightly on one of the sides, you get incomplete ones.
Well, if some of the functions go to 0, maybe one could get compactified to smooth solutions. They're not defined on the very line, but just on a half-line, say, but can be extended smoothly. Could that happen?
So actually, that was part of the reason I'm looking here at R cross S. So essentially, I'm assuming that my orbit space is R, right? Is because really, if my group, say, is nilpotent, which originally I was looking at this for nilpotent groups, then I was assuming nilpotent and simply connected, so I can't have any isotropy because my maximal compact subgroups are going to be trivial. And so that's going to force my orbit space to be either R or S1 rather than a half line. And then I chose R over S1 because there's a theorem that was proven by Bugallo, Rimoldi, and Setti that says that if your soliton potential in the expanding case is bounded, then and you're complete, then you must actually be Einstein. So I need my soliton potential to be unbounded. And since it's essentially a function on the base with the S1, of course, that can't happen. So really that, at least in the nilpotent setting, forced me into this R, the case where it was, my base was R, the real line. So, yeah.
Can you do any numerics for these kind of equations to see what happens?
I perhaps could. I must admit I'm not definitely nowhere near an expert in numerics. Yeah, so about as far as the best I can do on computers is plotting the phase portraits and things like that. I would have to speak to someone, get some help with numerics.
Okay.
But of course I could do that.
Thanks, very nice talk.
Any other
Okay.
questions?
Okay, hello. Could I ask a question?
Yes.
Okay, so thank you very much for very interesting talk. And I'm not a specialist on Ricci solitons, but I'm engaged in nonlinear partial differential equations and soliton equations, Skirm family models, and I invite everybody to visit my website. I have given the address on chat. And my question may be considered as naive. However, I'm very intrigued with the name Ricci soliton. Now, my question is about why soliton? Because, in other words, which solitonic properties the Ricci soliton possesses? We distinguish topological solitons, for example, in Sine-Gordon model, yes, on non-topological solitons in KdV equation, and so far and so far. And so Skirmion, for example, can be considered as topological stable soliton solutions. So what about the solitonic properties, if any, in the case of Ricci solitons?
So I don't actually know too much about the origin.
Do you mind
the-
if I jump in, Alan? I
Yeah,
think
I
I
would
can
love
comment on that. So this
Do you
name was
know?
coined by Hamilton, who invented Ricci flow back in the 80s. And of course, the name, the soliton, was already taken by people from the wave equations, right? Hyperbolic PDEs to denote solutions that evolve translating or in a self-similar way. So these parabolic soliton solutions, yeah, like, I mean, what's a soliton wave, right? It says it's a wave that doesn't change its shape when it evolves under the PDE, or at least, you know, intuitively speaking, I'm not saying anything precise, but in this parabolic case, these Ricci solitons have a similar property, namely when you evolve by Ricci flow, the geometry up to rescaling does not change. I mean, the metric, if you write it in coordinate, it can change dramatically, the way the metric looks written in coordinates, but then geometrically, everything stays the same. So that's why then, I mean, morally, they're sort of a similar thing, but in the parabolic setting.
So maybe the second question, because Adam Thompson has said, among others, about the unstable manifold. So whether the instability of a manifold has common anything with stability of Ricci soliton or not? What does the unstable here means? Unstable
in this
with respect
case,
to what?
in this case, it won't have anything to do with the Ricci solitons and their stability. So with the Ricci solitons, when Ramiro talks about them evolving, I've always considered so static equations. So there's an equivalence between some kind of static equation and then this dynamic condition of evolving self-similarly. And so when I talk about this parameter S, that's like a spatial parameter, not a temporal parameter. But so unstable here, I think it just comes kind of dual to stable. So within your ODE solutions, if you linearize at a stationary point, you can look at all of the solutions that converge to this stationary point as your parameter goes to infinity. And so you call this, right, the stable manifold, and then perhaps the unstable manifold's like dual to that. So it's the solutions coming out of a stationary point. So if you reverse time, or if you send, you reversed your parameter, or you send your parameter to minus infinity, then you converge to the stationary point back in time. So I guess that's what's unstable about the manifold. It's the solutions that are leaving the stationary point.
Okay. Many thanks. Thank you very much.
Any other questions? Actually, I have a question. If you start with an Einstein solved manifold to start with and do your construction, is there anything special that happens in that case? Or
so I guess in that case, if my S was Einstein, sorry, is that this S, then it would become just a Walt product ansatz. Sorry, I'm not thinking correctly. I'm not sure. So in that case, then if I look, yeah, sorry, in that case, I think it would be more akin to a kind of Walt product.
S is
ansatz,
unimodular
just
here.
because. Yeah,
oh, okay. Yeah, so my question doesn't make sense.
Yeah, so I wanted S like unimodular for something to work later on. But even, yeah, like if you just, because you could set up the equations, but I think if you set up the equations, it would just not give something quite as interesting, perhaps.
Yeah, no, I'd forgotten about the unimodularity, so I think my question doesn't even make sense. So, okay. Yeah, well, thank you very much.
Thank you.